So one popular simple lab exercise that you can do in an intro E&M course is to take two pieces of tape, put some electric charge on them, and then watch them attract or repel each other. And two ways that you can put charge on them is you can put them together and then rip them apart, and that will give them opposite charges so that they attract. Or you can put them both on a table surface and rip them off, and then in principle that should give them the same charge, and then you can watch them repel. Well, here I've got a simulation for you that recreates that experiment. So we've got a piece of tape on the left, a piece of tape on the right. And so we're setting those up just with two box objects here at the beginning of the code. And we have to set up an anchor point so that they can rotate around the point up here. Presumably you're holding them with your fingers up here. Then down here we get to define our constant. So Q here is the amount of charge that's on each of these. And this is going to be in made-up units for this video. You can implement real-world units at the end of the video. But we'll just give a Q of 1 for right now. We have to give an epsilon naught value. This is that universal electric constant for the universe that just tells you how well the universe conducts electric fields, more or less. And then we have to get the area of the tape, because the larger these pieces of tape are, the smaller the force is going to be between them, because obviously that's more charge. That's the same amount of charge distributed over a greater area. And then down here we calculate the magnitude of the force between the two. And it's a surprisingly simple equation because the geometry works out nicely if you apply Gauss's law, where you just take the one charge times the other charge. So here we're assuming that the two charges are the same. So you might need to make charge values different. But it kind of doesn't matter because it's just going to be one charge times the other. So you might as well just represent it as you know, some number in here. Then you divide by 2 times the area times epsilon naught. And so this is just the electric field of a sheet of charge multiplied by the charge of the other object. So that's why it's Q squared instead of Q. And the way this is set up, if you make this a positive number, then the two tapes are going to repel each other. And if you make it a negative number, then they have opposite signs and they are going to attract each other. And since you're holding these things up like this, there's also a gravitational force acting on it. So we need the value of the Earth's gravitational field. So this is going to be gravitational field magnitude. And then here you just have the mass of each piece of tape. Cool. And then we're looking at these things. Technically, they are rotating, right? Because we're fixing this end and they are attracting each other or repelling each other. And then gravity is also acting. So we need to keep track of their rotational velocity omega. So this is the left omega and the right omega. For our example here, they're going to be the same. There's not really a whole lot you can learn from making those different, but you can if you want to. So I've left those as separate variables there. All right, so we come down here into the animation loop, and since we are dealing with rotational motion, we need to concern ourselves with the torque. We calculate torque as the cross product between the position vector of the point you're looking at and the force that you're looking at, the force vector. So let's take a look at this position vector. This position vector, we need to go from the pivot point to the center of the tape. So that's where we're taking left underscore tape dot pause, that's the center of the left piece of tape, minus left anchor, that's this pivot point up here. That gives us this R vector that we need to go in here. And then we cross that vector with the torque, with the force of gravity, not with the torque, the force of gravity. So we just have the mass times the gravitational field times the down vector. Pretty straightforward stuff. Sorry, Brian, go back for that. Pretty straightforward stuff. You have seen that in your intro mechanics course. And then we need to add to that the torque due to the electric force between these two. So again, we take the same R vector, because this is the same. We're concentrating the forces on the center of the tape pieces, crossed with this force vector. So here we've got our force magnitude that's taken care of up here. And then we've just got the direction. That's all hat means. It's just we're getting the direction, the unit vector. And we take right tape dot pause minus left tape dot pause. We're getting the vector going from one to the other. And so this is going to be more or less consistent depending on if these things are out of sync. If these things are in sync, then this should always be left or right. But then this thing, the r vector, is the thing that's changing as they rotate back and forth. And so the gravity force is going to tend to make them rotate toward equilibrium, and then this force is going to tend to pull them together or push them apart. And so really they're oscillating around an equilibrium point there. And then we just use Euler-Kromer to update the left tape's omega. We just add to it the left torque.z times dt. So here we're just assuming a moment of inertia equal to 1 for simplicity. You could put in the actual equation for moment of inertia, but it's just going to change the speed of this thing. It's not going to make it suddenly flip around and do somersaults or anything. So we're just picking units to make this setup easier. And then here we repeat the same process for the right piece of tape. We just replace every left with a right. That also means we're flipping left and right here for their relative position vector. And then we update the right tape's omega value. Then we come down here and we use VPython's rotate function. This is a handy function that just takes care of rotating. All you have to do is tell it the origin, so that's the point you want it to rotate around. That's why we bothered to define that left anchor and right anchor before. You tell it how much angle you want it to rotate through. In our case, that's going to be omega times dt, giving us the delta theta. So this is the second step of the Euler-Kromer method, kind of in disguise. And then you tell it what axis you want it to rotate about. And for us, that's just going to be the z-axis, because we want these things rotating in the xy plane. And so you get this nice little animation that shows you the attraction or repulsion. Let's see what happens when we flip this from repulsive to attractive. So we start out with the pieces of tape hanging vertically. They get pulled toward each other. They rotate back down this way, but then they want to be pulled toward each other again, thanks to the attraction. So we get a little bit different result here. You can see they're tending to be pulled toward each other more, whereas if we make it repulsive, let's make this a positive sign. Now they start out flat, they're getting pushed away from each other, and then they swing back this way, and then they can't get past that vertical orientation there, and so they are getting pushed away. So we can see the attraction versus the repulsion here. And you could actually get out and measure this angle if you wanted to. I'm not sure how well it would match up with your tape experiments. If you wanted to use this as a means of determining how much charge you had on there, you can probably use that to get a decent order of magnitude, but it's probably not going to match the angle of your tape pieces exactly. And then of course we can change the charge. This is the thing you would fiddle around with for an experiment. Let's suppose I give it a really good rip and make it 10 times the amount of charge. Now we get a ridiculous amount of repulsion there. I don't think that's going to happen in your experiment. So we probably want this value to be between 1 and 10. Let's try 5 maybe. There we go. So for 5, we get over a right angle there. I wonder what charge value you need in this made-up system to get a right angle. So let's try 3. Let's see. That is getting us decently far apart, but it's not yet a right angle. So let's split the difference again and get 4. It's like a bird flapping its wings. It's a good way to animate wing flapping, I suppose. All right, so we need to go a little bit higher than 4. We need to go between 4 and 5. Let's try 4.5. My guess is that's going to be too much. Oh no, that was actually just about perfect. Wow. That's pretty good. I'm going to call that good there. So let's just make a little note here to ourselves that Q equals 4.5 gives a right angle tape flap. And let's turn this back to 1. Let's make this a little bit more reasonable. But yeah, you could use this alongside of this experiment to kind of, validate the kind of behavior that you're seeing, get an idea if you're seeing attractive or repulsive behavior. Anyway, I hope this is a fun activity for you. Thank you so much for watching. I will see you next time. Bye-bye.